Somewhere in California, inside a building like this, there is a room kept 50 times colder than the void of deep space. In the autumn of 2025, researchers here announced a result. Their machine spent 2 hours working out a single value. To reach that same answer on the world's fastest supercomputer, the estimate is 3.2 years. The hardware responsible is Google's Willow chip, an array of 105 superconducting circuits, or qubits, etched into a piece of wiring. But the scale of the achievement is actually found in the 40 qubits they deliberately left turned off. In the actual research paper, that 13,000-fold speedup wasn't set using all 105 qubits. It was set using exactly 65. Stepping down to 65 is a hard requirement of the physics. This is what researchers call the usable volume of a chip. To get the depth required for this calculation, they had to trade away the width of the array. Go any larger and the accumulated noise would have destroyed the signal before the 2-hour mark. 65 is the crossing point. It is the precise architectural limit where the quantum hardware succeeds, but the math required for a conventional machine to follow it begins to fail. The machine measures a physical property of chaos. It tracks exactly how fast information scrambles and hides within a closed system. This quantum echo has 4 steps. First, the chip runs a complex sequence of operations, evolving the state across the 65 nodes of the array. In the middle of this chaos, the researchers reach in to apply a nudge, flipping the state of a single qubit. Then they run the exact inverse of the original sequence. The system flows backward toward the beginning, but that single nudge has been amplified. The return journey is no longer a perfect undoing of the outbound one. The machine measures the gap between where the system should have returned and where it actually arrived. That gap is a measurement of the quantum butterfly effect, the speed limit at which reality is permitted to scramble information. Why does this fingernail-sized chip defeat machines that can simulate a nuclear detonation? It comes down to the raw arithmetic. To describe 65 interacting qubits exactly, a computer needs to track 2 to the power of 65. That is a list of complex numbers 37 billion items long. Storing that list would require hundreds of exabytes of memory, more storage than exists in every major data center on Earth combined. Supercomputers usually use compression tricks to ignore unimportant data, but this experiment triggers the sign problem. Quantum paths cancel each other out in ways that make the noise mathematically indistinguishable from the signal for a conventional machine. At 65 qubits, the calculation becomes incompressible. There are no shortcuts left. Google spent 10 person-years trying to break their own result before they announced it. They tested 9 separate classical algorithms, hoping to prove that a normal computer could still handle the workload. They were right to be skeptical. A previous milestone from 2019 was eventually matched by conventional computers in just 6 seconds, once researchers found a way to compress the data. This time, the counterattack failed. Independent researchers proved that this 65-qubit circuit resists every known form of classical compression. The calculation held its ground against the hardest stress tests the field could design, confirming that the quantum advantage was real. For 400 years, the deal underneath science has been simple. You make a claim, and another person independently goes and looks. They check the math, or they point their own telescope at the sky. The 65-qubit result exists in a regime where no human pencil or conventional machine can follow the logic from start to finish. The sequence has been broken. The machine gives us a truth about the universe, but we lack the means to confirm the work. When asked how this answer could be checked, the researchers named exactly 2 things capable of doing it. The first is another identical quantum computer, but if 2 machines share a design flaw, they will be wrong together, perfectly and confidently. The second witness is nature itself. The universe runs this same computation continuously in its atoms and stars, and it has never made an arithmetic error. We have moved from checking the answer to checking the machine. We are now building devices that can tell us the truth, while leaving us with no way to know it.